heterogeneous agent macro models. This is joint work with Jojo, who is here, who's a pre-doc at Princeton, and I strongly encourage everybody to accept him into a PhD programs. He's an excellent pre-doc. And also Matu and Sebastian. Okay. All right. So I think this conference is in part a testament to the enormous progress that's been made in using deep learning to solve discrete time heterogeneous agent models. But I work in continuous time. And so the spirit of this project is to try to think about whether we can make similar progress trying to solve continuous time models. And the models we have in mind are ones with heterogeneous agents, aggregate shocks, long-term assets, portfolio choice, illiquidity, all these kind of things. We want to think about whether or not we can, so in the maths literature, you call this a so-called mean field gain. We want to think about whether we can deploy these continuous time tools and the neural network tools and find a way to solve these models. All right. So for what I'm going to talk about today, there are going to be sort of two main steps in trying to do this. So the first is we have to think about how do we want to find a finite dimensional approximation to the distribution. And here I'm going to discuss thinking about replacing it with a finite collection of agents, and also how we might project it onto a set of basis functions. And then the second step is, once we have this high dimensional approximation to the distribution and the PDEs that evolve from that, how do we use neural networks to solve them? Right. In terms of what I'm going to show you, how am I going to test it today? Well, I'll take the standard route and compare it to Kruszar-Smith and some of these canonical macro models. And then in the end, what are we trying to do with it? What's the economic question we're trying to answer? Well, the follow-up project that I'll also talk about today is really trying to understand the impact of housing policy on inequality. All right. So in terms of the structure of the talk, so I want to outline the technique in, I think, the simplest form of the model, baseline macro model you learn in a first-year course, the Kruszar-Smith model. So I'll go through that first. Kruszar-Smith has a number of features that make it particularly easy to solve. In particular, the market clearing conditions are very easy to work with. So then after that, I want to do a different example. We have a more complicated market clearing condition. We have long-term assets, and life's a bit harder. So we can show how this technique would generalize. Okay. Are there any questions so far, or should I dive into it? I guess you'll interrupt if you have questions. Okay. So let's start with the Kruszar-Smith model set up in continuous time. And I'll use this to illustrate the sort of general way we're going to solve things, and then we'll enrich it later. So I'm going to think about a continuous time, infinite horizon economy. It's going to be populated by a continuum of households. They consume goods, they supply labor, and they save into claims on the aggregate capital stock in the economy. There's going to be a representative firm. The representative firm rents capital and labor to produce goods according to a Cobb-Douglas production function, where K is capital hired, L is labor hired, and there's a stochastic productivity process driven by the Z, which is the only exogenous aggregate state in this economy. We can see here that it's going to be a mean reverting TFP process, where this dB naught is the common Brownian motion that's driving through this economy, and it generates a filtration FT. You look like you have a question, or maybe not. You're sort of halfway in between asking.
Yeah, so continuous time versus discrete time. If the time interval goes to 0 and the discrete time model converges to the continuous time model, then they're basically the same, and it's a matter of what's more convenient, right?
Yes.
So why should we make a big deal about discrete versus continuous?
I think that's so. I think there's.
My objection is that there are a lot of things about continuous time that are extremely hard to figure out how do you calibrate it to actual real world data, microeconomic data or macroeconomic data.
So I think the bigger, so two comments. So first is the way you would solve them is different, right? Because continuous time ends up being all about derivatives, whereas discrete time is all about calculating expectations.
No, so there's difference equations and differential equations.
Sure.
You could solve different, they're total parallels for everything. Hamiltonians versus value functions. Everything's parallel if the problem is one where the discrete time converges to the continuous.
Talking about the computational algorithm, but yes, of course you have some convergence. In terms of what I'm going to do today, I think the big advantage of continuous time is you get very clean portfolio choice problems. So in discrete time, you end up with a collection of Euler equations, and you have to work out how to handle these Euler equations. In continuous time, you get closed form solutions to portfolio choice.
Fine.
So when we get to these problems and the assets,
Okay.
it's going to make life a bit easier.
All right.
But
That's your trick.
numerically, I mean, if I can go to 30 seconds, there are big differences.
Oh, huge differences. Yeah.
There are huge differences because once, I mean, essentially the way you solve the continuous time models is that you have to discretize this. It's true. At the end of the day, what you are solving is always a discrete time model. But the difference is that a continuous time, continuous space model maps into a discrete time, discrete space model. So any continuous time model ends up being solved by a discrete time, discrete space model. Whereas a discrete time, continuous space model, you have to deal with a discrete time, approximate the continuous space model. And that is much more that's much more problematic because you get issues about grid points, interpolation, computation of expectations. In continuous time, essentially, when you discretize, there are only two possibilities. If it's a diffusion, you can only move one.
Sorry, but in
No. I'm giving a seminar. Maybe I will, rather than you guys getting into a long debate, I'm going to continue. Okay, so you guys can talk over lunch. This is not a discussion club. Okay, all right. All right. So we're going to do continuous time. All right. So this is the production technology. Then in terms of the markets, we have really only three markets in this economy. We have a goods market, which will be the numeraire. We have a capital market with a rental rate, and we have a labor market with a wage. Okay.
So how can you say you're doing a Purcell-Smith model? They have an aggregate shock that goes from a level to a different level and then back. It's a Markov. It's not a continuous time shock.
So it's an adaptation of the Purcell-Smith model with a continuous movement in the aggregate state.
That's totally different from Purcell.
Chris, you're close to your budget.
Okay.
Do you have some philosophical objection to solving a continuous time model?
Yes, I do. I think it's
Okay.
I think so.
Let's move on.
That might be a discussion for later then. Okay. All right. All right. So we need to set this up. So let's start with the household problem. Okay. So each household in this economy is going to have two idiosyncratic states, as I think you guys are probably aware. So one is going to be their idiosyncratic wealth, which is this A. The other is going to be their idiosyncratic labor endowment, or whether or not they're working. So what do the agents do? Well, given the belief they have about the price process in the economy, the household is going to choose consumption to maximize the present discounted value of their utilities, subject to the law of motion of these things. So the law of motion of wealth, well, it's a standard budget constraint. You get wage income, you get a return on your investment, and then you take away your consumption. And what's happening to this labor endowment? Well, the key feature of the Purcell-Smith model is that your labor endowment is idiosyncratically stochastic. So you're moving from employment to unemployment at an idiosyncratic Poisson rate. And the whole difficulty in this economy is you cannot ensure these idiosyncratic employment and unemployment shocks. And that's what's going to sort of drive the dynamics of the model. Okay. The other key feature about this is there's a limit on your borrowing. So your wealth process cannot go below some lower bound A bar, and that's kind of the financial friction in this world. Okay. So what we get coming out of this is the combination of the agents getting hit by idiosyncratic labor shocks or employment shocks, and the fact there's a financial friction and there's incomplete markets, means that a distribution of agents is going to emerge in this world. So you're going to let capital V be the population distribution over time, or the cross-sectional distribution of the agent states. Will that little g be the density? And these are really conditional on a particular history of aggregate shocks. Okay. So that's really the setup of the model. That's the environment. And then this is the problem that the household solved. What would equilibrium look like? Well, if we want to define the equilibrium here, we say given an initial density, the equilibrium consists of a whole bunch of stochastic processes for consumption, the distribution across agents, and then these two prices, which are grouped together with this Q notation to be the vector of the two prices, the rental rate on capital and the wage rate on labor. So we have these objects, and then we need to have that given the beliefs of the price process, the households optimize their choice of consumption. Given the belief about the price process, the firms optimize their hiring of labor and capital. So this means that the firms set the marginal product of capital equal to the rental rate, and they set the marginal product of labor equal to the wage rate. And then finally, we have standard looking market clearing, where we have in the capital market, the total capital out there is equal to the wealth of all the agents. And similarly in the labor market, the labor supplied by all the agents is equal to the aggregate labor hired by the firm. And then finally, we need to have belief consistency. So we set this up saying, given beliefs, the agent's optimized. So it's a rational expectations equilibrium. So it needs to be that agents are correct about the stochastic process for the prices.
So no jumps, no jumps.
No jumps in the aggregate state.
No jumps in the continuous time. You can do jumps, but you're not doing jumps.
So you have jumps in your labor endowment, right? So your labor.
No. Keep going.
So your idiosyncratic labor endowment is jumping.
No, I mean jumps in wealth.
And no, there are no jumps in the.
Jumps in wealth, no jumps in wealth. That's what I was trying to
The
get.
law of motion for individual wealth does not have a jump.
Okay.
All right. So the first thing we can observe about this Purcell-Smith, this setup's really nice, in the sense that we can combine the first order conditions of the firm and these market clearing conditions to get closed form expressions for what the prices look like in terms of the aggregate state Z and also the distribution G. Okay. So if we put everything together, we get that the wage rate and the rental rate are just the marginal product of capital, where capital is just the first moment of the distribution. This is the feature of Purcell-Smith that makes it a very tractable problem to try to work with. And we'll use that in this first part. And then when I go to the second model, we'll talk about how we can generalize the approach. And we don't have this very nice sort of setup where the prices are essentially closed form solutions of the distribution. Okay. So the idea of this approach is to set it up recursively and work with the differential equation that emerges. Okay, so in the mean field game theory literature, this would be setting up the so-called master equation or big differential equation for the whole system, and then working out how to approach that. So to do that, we need to think about what the recursive formulation of the problem would look like. So at the aggregate level, we have two states. We have aggregate TFP, and we have the distribution of agents' wealth and labor across the economy. Individually, of course, we have their wealth and their labor. And so when we think about the household value function, it would have four inputs. We'd have the two idiosyncratic states, their individual wealth and labor endowment, and then also the aggregate TFP and the distribution across the economy. Okay. Yeah, go for it.
People know that partial differential equation has twice differential solution, or supposed to be based in advance.
It's a great question. So this is really what Moll kind of works on extensively in his work, mathematical work on this equation. The difficulty here is we have this constraint, right? So we have some boundary on how low A can go. And so if you work through this, you find that it's a classical solution on the interior, but then at this boundary, you have this inequality. So essentially, it's a viscosity solution at one point. But as I'm about to talk about, in everything we're going to do, we're going to replace these inequalities at the boundary with penalties so that we can get it to be smooth all over, which is going to make it a lot easier for the neural network to handle. I would strongly recommend that you really want to make sure that you have derivatives everywhere before you start to try to neural net.
Edward, you said models, derivatives are terrible. They're hard. Kinks, discontinuities are the essence of heterogeneous agent models. Discontinuities and kinks are the essence of heterogeneous agent models.
I'm going to take that as a comment.
It is a comment.
Okay, so we can set this up recursively. So once we have it recursively, the agents are going to choose consumption to solve this HJB. This has a bunch of standard elements, right? So you get your flow utility. This is the derivative of your value with respect to your wealth. This is the law of motion for your wealth. This is what happens when you jump, right? So your individual labor can jump. This is the change in your value. Then we have the influence of the aggregate state. And then we have this extra term, a participant has enabled closed captioning. Okay, no problem. I don't know how well that works, but okay. So, the only term here that's non-standard is this extra term, which is the derivative of the value function with respect to the distribution. And this is the term that's caused people so much trouble in the macro literature, because this is an awful derivative, right? We have to do it as a so-called Wasserman derivative in the mean field game theory literature, and it's a complicated high-dimensional derivative. Okay, but other than that, it's a very standard-looking HJB. What about, so that explains how people optimize, right? The HJB governs the way individual agents optimize in the system. What about what happens to the evolution of the distribution over time? Well, we have that for any policy rule, or for the optimal policy rule C, we can think about how the distribution evolves with the Kolmogorov forward equation, where here we have the drift of the states, and here we have the agents going in and out of unemployment. And then again, in equilibrium, we need to have that agent's belief about the law of motion for the distribution is actually the correct belief. That's the rational expectations. Okay, so this is the recursive setup, right? We can see it's essentially a collection of an HJB given a belief, the law of motion of the distribution, and belief consistency. As I was just mentioning, the first thing I would say about this is that working with an inequality constraint and having a discontinuity on the boundary is a huge pain. And so for all the problems I'm going to do today, whenever we have something like an inequality constraint or an inequality boundary condition, we replace these by penalties in such a way that we're going to get a smooth value function. Okay. So that's our setup. We want to reduce this down to one differential equation. So here we'll borrow some tricks from the maths literature. So what we can do is we can take our KFE in equilibrium, the evolution of the distribution. We can take our market clearing conditions, our belief consistency, and we can put all of this into the HJB. And that gives us one differential equation that essentially governs the equilibrium value function in this economy. So borrowing the term from the maths and physics literature, this is a so-called master equation for the whole economy. Okay. So here we get this one equation. We have the same components, and we're going to try to solve it. So our goal here in this paper is to try to work out how can we attack this problem? How can we try to find a solution to this equilibrium value function for the economy?
But one very good question.
Yeah, go for it.
If you have a multiple agent, I mean, in addition to the heterogeneous agent, you have other agents.
Oh yeah, exactly type differences.
That can be also incorporated into a master
It's a
equation.
great point. So then you would have to have that the V has a subscript I for the type of agent. And so what we do in that case is we would parameterize it, right? So suppose you have different agents that have different borrowing constraints, right? Suppose that this A is indexed by a type of individual. Then we would include that as a parameter in the value function, essentially. And when we take it to the neural network, we'd have an input into the neural network to be what this A looks like. And that's how we handle that. So in principle, yes, you would have a master equation for each type of agent, although it's probably easier to think about it as kind of a state variable is not moving around. Does that make sense? Okay. So if you look at this master equation, I think you can see pretty quickly what the problem is. Right? The problem is we have this awful looking derivative here. It's coming from the fact we have this continuous distribution moving around in the economy. So we're going to have to handle that. Okay. So we want to solve this. And really it's sort of three main ingredients. The first ingredient is we need to think about what is a finite dimensional approximation for the distribution. Okay. And I'm going to talk about briefly two options, and we spend more detail in the paper talking about them. One is to replace the continuum of agents by a finite population of n agents. And the other one is to project the distribution onto a finite dimensional set of basis functions and then keep track of the coefficients in that projection. They're really your two main options. Once you've done that, we end up with a finite but very high dimensional approximation of the system. In that case, we need to use a high dimensional tool. This is where the neural networks come in. So then we approximate the value function by the neural network, and then we train it to try to minimize the residual in the master equation. Does this make sense at the high level? So I think in some sense, this is the most direct approach to trying to attack the continuous time problem with the neural nets. Okay. I just want to make a couple of more detailed comments on these ingredients. So the first is the finite population versus the projection. So what are the differences? You have to make some decision about how do you want to do this approximation in the system. So first of all, there's a question about what does the distribution look like? Well, if we work with a finite population, the distribution is essentially replaced by the position of the n agents in the system. Right? And we're going to keep track of what the position of all these agents is. If we wanted to do a projection, we would choose a fixed set of basis functions h, and then we would project the density onto that set of basis functions. And so in that case, what we keep track of is this alpha t, right? The coefficients of this projection onto the basis function. So that's really the main difference between handling the finite population versus handling a projection style approach. Yes?
Why don't you consider the Yang thing?
But,
The Eric Yang thing, approximate distribution.
Yeah.
That is, I think.
by discretizing.
Yeah, but not by, so finite collection of agents is bad to the discrete time is horrible because the low version is fine. So if you discretize distribution.
Yeah, that's really a type of projection, right? No, I project them as an indicator functions for a discrete state space. Right? Okay, I would nest it in that. I would just say that's like indicator functions for a discrete state space.
Finite projection is a pompous way of saying it, to be honest, because it makes much more complicated. So just discretize. Of course, you can.
That's fine, but that's not the only option you would consider, right?
I'm just saying that it's proven extremely efficient in discrete time in many applications.
Sure.
I'm wondering why you spend time trying to find alternatives.
So why would we not just go with a discretization of the
Yeah,
spaces?
standard
Okay, fair enough. So I think, my comment on these two things is the finite agent approach has difficulties with a small sample size, particularly if you have ex ante type heterogeneity. The difficulty with all these projections is you have to then get a law of motion for these coefficients. So if it's a discrete state space, you have to think about how do when you discretize the state space, how do you think about a law of motion for the movement of mass between these discretes? So you can do it with finite difference, and we do that example in the paper. We use a finite difference approximation to get that. If you think about G. Huang's paper, he does a finite volume method to get a similar thing. I think all our experience is actually that's pretty hard in the sense that it's not easy to get, but once you do this discretization and then you try to get a law of motion for these coefficients, it ends up being actually quite tricky to try to get that to work well. In that sense, the finite agent is often easier. So I think the trade-off is the small sample size versus the complexity of the approximation to the common approach. So in these kind of Kruskal-Smith models, I actually think in some sense the finite population works very well. But if you're working in a model where you have to have a very complicated equilibrium condition, and you really need to know a lot about the shape of the distribution, then I think doing some kind of projection or finite state space works better. So Yucheng's going to present a paper on search models tomorrow, and for that, I think doing some kind of finite state space approximation or projection is a lot better than the finite agent. So I think really to think about which one you want to do, I think you need to look at the market clearing conditions and think about, do you just need a moment of the distribution, or do you need to really understand a lot about the curvature of the distribution to be able to clear the market? I think that's really what governs which approach you want to do with this.
So I object to you using the term Kruskal-Smith model. A continuous time model like the one you have solved simply is not very similar to the Kruskal-Smith model.
I'm not very worried about terminology. What would you like me to call it?
I don't care what you
The
call it.
Payne model?
You're not call, if you're going to call it Kruskal-Smith, show me that the
No.
show me that the
What would you like?
the decision rule of consumption as a function of assets is arbitrarily close to the Kruskal-Smith decision rule.
Yeah, I'm not interested in
not
this question. Just tell me what you'd like me to call it. I'm
I
interested in the model I wrote down. So what would you like me to
Don't
call
call it Kruskal-Smith.
Yeah, what would you like me to call it?
Can you please inform me?
Okay. The model, the canonical macro model. Okay, I'll call it the first year macro model instead. Okay.
No, for people who do it continuous time. They're very different.
All right, so what about this algorithm? Okay, so let's highlight the key features of this algorithm. So yes, we're going to take some neural network approximation to the value function. Okay, so we're going to approximate it. We have some set of parameters that are in that approximation. How are we going to work? Well, we start with some initial guess of the parameters, and then we're going to update. So in each update step, we're going to start with we take a random sample from the state space, then we calculate the weighted average error. Okay, so we calculate the loss in the master equation on our sample, and then we also tend to impose a collection of shape constraints. For example, penalize non-concavity, or we build these kind of shape constraints into the structure of the neural network. You can do it either way. But we do find important to make sure we penalize to try to help the neural network find the right shape. Then we update the parameters using stochastic gradient descent, that I think everybody in this room is very familiar with. And we keep doing this until the loss in the master equation is satisfactorily small. Okay.
Can you just comment, so like, you shape this equation in one dimension?
Yeah.
How do you do that in multiple dimensions?
Yeah, it's a good question. So, for example, with respect to the aggregate shock, for example, so there sometimes we actually put a constraint on the sum, right? So we found that the Kruskal-Smith model was helpful to force the neural network to realize that consumption or aggregate consumption was going to have to move with the aggregate shock. And so sometimes when there's a lot of complexity in the States, is sometimes put a shape constraint essentially on how the aggregate is going to respond. And that's another way of handling it. Yes.
Two quick questions about the weighted average.
Sure.
So first is, I mean, but maybe it was in the master question, but I didn't pay attention. But how is the boundary condition introduced in the master equation?
So we've taken out the boundary condition, we replaced it by a penalty, so that if A gets below a lower bar, you start to pay a penalty to try to get the problem to be smooth, right? We don't want to have this kind of, so we spent a lot of time trying to solve the model with the inequality constraint. Turned out to be very difficult, gives too much flexibility to the neural network, and sort of has this problem that the master equation is not all that well defined on the boundary. So we switched away from that. If you did have boundary conditions, then we would do extra sampling on the boundary, and we'd add an extra penalty for the boundary condition.
Okay, then as an extension of this, and then for the upper, I mean, you are solving it in a complex. Are you imposing some upper boundary condition in the model, or
there's a free boundary condition of the upper boundary in the process model, in the sense you would eventually start to disable. And we don't impose, we don't try to impose kind of an upper boundary condition.
So I mean, if you were solving by finite difference, you will have to impose it, but here you don't need to impose it.
So what happens, so the most common finite difference solution is the upline scheme. And the upline scheme says, you know, you choose whether to use the forwards or backwards derivative based on where the drift is going. And so in that technique, what happens is as you get towards the high A, the drift of A starts to go negative. So you always pick the backward difference approximation. And as A gets towards the lower boundary, you would pick the forward difference approximation. So in that sense, so long as your range is sufficiently large, the way you've kind of specified the upline scheme means you don't actually have to have a boundary condition at the upper boundary. It's just because it's eventually a reflecting boundary, as long as your range is big enough, it would work. So actually there isn't an upper boundary in these classic finite difference solutions to the Agari model, for example.
And then do you ensure somehow that the transversality condition is satisfied? Because the transversality condition is also lurking behind. I mean, you have this, that the limit of the exponential of minus rho t by the value function should converge to zero, because there are solutions that satisfy the Hamilton-Jacobi-Berman equation and violate the transversality condition.
That's a good point. So no, we don't explicitly try to satisfy the transversality condition. What we try to do is put penalties to rule out those solutions. So I think you would say, I think indirectly, there's a lot of stuff done in this literature, from imposing penalties to trying to use kind of time-dependent updating. There's a lot of things people do that I think are partly sort of fixes to try to rule out these solutions.
How does it work? I mean, so what is inside this epsilon f?
10 minutes, the epsilon f. Well, that really depends on how you want to do the constraints. So suppose it's an issue with non-concavity of V, then this would be, you know, you would calculate the derivatives of the value function on this sample, and then you would penalize it if the derivative is in the wrong direction, for example. Okay, so I'm going to do a little bit of Q&A. These are some common questions I get. So what type of network architecture do we use? Well, for the finite population, we keep it pretty simple. We're really just using a feed-forward network with 5 layers, 64 neurons. It's true that we found projection harder, and I think this is going back to the discussion earlier, but it's kind of hard to work with this approximation to the Kolmogorov forward equation. And here we did use a type of recurrent neural network. We borrowed tools from the deep Gallatin papers in the physics and maths literature. We talked about these differences in discrete time. I think the two big differences are, one, we really have to approximate derivatives rather than try to simulate and calculate expectations. I think that's a big difference in this algorithm compared to a lot of the discrete time neural network algorithms. And here we use the automatic differentiation to get automatic derivatives to evaluate the loss function. I think this is actually a big gain for the continuous time literature. Typically, one of the biggest problems for trying to solve differential equations is you have to take approximate derivatives like finite difference or something like that. This causes a whole lot of problems. I think in this sense, the automatic differentiation is a big help to the continuous time literature to solve this more cleanly.
There is no derivative if the function has a key.
Yes, but we're going to work with models without a key. That's important.
Yeah.
Okay, so we also have to choose where to sample. So here we borrow tools from Gautam's work, and when we think about doing an active sampling where we sample more where the error is, right? So again, we're not trying to just simulate. We don't just sample from an ergodic distribution. We kind of have to choose where in the state space you want to sample from. And we choose this strategically to try to minimize errors. Yes?
You first simulate and then among the simulated ones, you choose the ones with the high errors, or you never simulate.
Yeah, that's the first one, right? So you would start, well, so you wouldn't necessarily have to simulate. So we can calculate, we're calculating the loss at these different sample points, right? So we can see where the loss is high and where the loss is low.
Also, okay, you take a random sample and
Yes.
regardless you choose the bounds.
Yes, so we can choose where to sample, right? So we start with a completely random sample, say like a Latin hypercube over the state space. And then we calculate these errors, and this is an average error across the sample. But we can also look at, on these different points, where is the error largest? And then we can increase sampling in the next run where we have the large error. Yes.
But since the whole point is that the state space is high dimensional, right? Isn't this going to be a super high dimensional cube?
It's a high dimensional state space. I mean, this, yes. You might agree with it.
Essentially uniform very power. I mean, you're going to set is going to be very small, right? The hypercube. And so the uniform sampling seems to be, if you go back to 50 dimensions, it's very high probability you miss every single relevant point.
I don't know what you mean by miss every single relevant
Well,
point.
so how big is the sample? Let's say a trillion. So if you have 50 dimensional state space, a trillion points fill up the tiny pretty uniform points, actually uniform. Fill up the tiny fractions of state space. So it seems that without simulation, you can't possibly get to accurate solutions.
So I think with the finite agent, we had more luck doing that. It's true that with the projection, we did end up doing a mixture of uniform sampling and then also simulating and getting the ergodic distribution and sampling from the ergodic distribution. There's nothing about the technique that rules out doing that. We didn't find we always had to do it, but we did find we sometimes had to do it. So I'm sympathetic to your comment. I think it makes a lot of sense to simulate.
So how many agents would you take?
So for example, say you take 40 agents, then that would be one example.
40, you say 40?
40, for example. You could go higher, but the
So
Lord,
it'll take 40,000.
you're not going to take 40,000 agents.
Okay, so it's 40,000 agents in the
Yeah,
finite.
but I don't think that's necessary. I think the
No,
Lord,
I agree with you.
so
That's why I was confused.
you only need the first moment. You only need the first moment. So
No!
Let's ignore it.
No!
Let's ignore it. Go on. I
So-
will understand.
if you have clearing conditions, where essentially the clearing condition is the mean, right? Then the law of large numbers kicks in pretty quickly.
Yeah.
If you have a situation where you care about matching, for example, like Yuchen's going to do in the search model tomorrow, then you care a lot about the distribution. In that case, I wouldn't use finite agents. I would use some kind of projection, and then you can do it at lower dimensions. So in some sense, this point you're discussing is how I would choose, whether or not to do it with a finite population approximation, or whether to try
I
to
think
fix
running out of time. It never came to the second model, you know. So.
Well, okay. All right. And then I'm going to move on. Okay. So we've got some comments there. Okay. So we compare actually to Jesus's work as the illustration of a good Chrysos-Smith solution, and we get it to be pretty close. Okay. I want to spend the last 6 minutes, I think I've got, according to my timer. I want to spend that talking about an extension of this model that we've been working on that works with clearing conditions that are more complicated. Okay. And I want to talk about how to do it, because I know there are some other papers on the program that talk about issues to do with portfolio choice. I want to highlight in some sense why continuous time can help us a lot in dealing with these kind of models. Okay. So the Chrysos-Smith model had this very simple market clearing condition. We can get closed form expressions for the prices. We now work with a more complicated market clearing. So to do this, as an example, I'm going to take a model from a follow-up paper I've been working on with Jojo, where we really study how housing policy impacts inequality when there's aggregate risk. So I'm not going to talk a lot about the economics of the model, but from a sort of computational point of view, there are two big changes that get introduced. So one is we introduce an illiquid asset, which is housing in this world. And the second is we have long-term equity, which we don't get a closed form solution to the price for. Okay. So let's set this up. Okay. So again, it's a continuous time infinite horizon economy. There's a consumption good produced by a Lucas tree. So we're going to drop the capital in the production and just go from a downward economy to keep things simple for this talk. So there's a Lucas tree that produces output in this economy according to a mean reverting process. Then we need to think about the assets. So there are going to be two types of assets. So there's short-term bonds and zeroing out supply, there's equity in the Lucas tree, and there's also housing and fixed aggregate supply. So two of these are liquid, right? So we have liquid competitive markets for goods, bonds at interest rate R, and equity at price Q. But housing, we're going to model housing as an illiquid asset in the sense it's hard or frictional to try and trade it. So we're going to say that if you trade houses at some rate iota, that incurs a transaction cost sum, right? So it's a frictional housing market. No, I'm not taking another question.
Okay, but that's the.
I'm not taking another question. I've got,
Okay.
So we have illiquid housing trading at a transaction cost side. And we're going to work from the start with a finite population of agents. The only difference to the utility here is that we get zeta times some utility benefit from housing. Okay. So we're going to add in this extra utility benefit from owning a house. And we're going to say that how much utility benefit you get from owning a house is going to be stochastic, right? It's going to be switching from a high benefit to a low benefit, which we interpret as a simple way of modeling housing need, right? What stage of your life are you in? Are you in the stage of life where you really need a house or you don't really need a house? And then finally, we're going to have a collateral borrowing constraint where the liquid wealth is greater than or equal to the amount you can borrow is some fraction kappa of the market value of the housing you own. Okay. So we're going to have something that looks a bit like a mortgage in the sense that you're able to borrow against some part of the value of your housing. Okay, that's our setup. Again, we can think about the agent problems. So we have idiosyncratic states. So now we have three. We have your individual liquid wealth in bonds and equity. We have your housing. And then we also have whether or not you have a high need for housing or a low need for housing. So what kind of part of the life cycle are you in? Again, given their beliefs, agents are going to optimize. Okay? So they need to choose their consumption and then also their portfolio and their housing to maximize utility subject to the evolution of all these states. So we have the evolution of the aggregate shock and then all these individual states. I'm not going to go into the details here. The nice thing about this, and I think this is a big advantage of working with continuous time in these kind of problems, is that we get closed form expressions for the portfolio choice. So as usual, we can get a nice Euler equation, we can get a nice equation for consumption. We can also get a nice clear expression for the bonds. We can get a very nice expression for the rate at which you trade houses. So this means we're not going to have to work with these Euler equations, these approximations through these Euler equations. We're essentially going to be able to take these closed form solutions for the portfolio choice and the asset market clearing and substitute them directly into the master equation. This is going to make our life a lot easier in terms of trying to solve this model. So equilibrium is standard. I'm not going to dwell on it. But what I do want to talk about is the difficulty of having the long-term asset. Okay? So it's helpful here to define the derivatives of the value function. So what ends up showing up here is the derivative of the value function with respect to wealth and the derivative of the value function with respect to housing. These are your two marginal values that are really important. Given that, we can get a nice expression. We can get a closed form expression for the interest rate, and we can get a closed form expression for the price of housing. So for this, it looks like the Christos-Smith, right? We get nice closed form expressions we can work with. That's sort of very similar to what we had in the previous model. But for the price of equity, we do not have a closed form expression. It's only implicitly a function of the aggregate state and the distribution. So that means when we set up our master equation, we substitute in our law of motion for the distribution, market clearing, and all this pricing, we're left with something that's only an implicit master equation. It's still got this object, Q, an unknown function of Z engine. Okay. And that's kind of the big difficulty and the big change in this algorithm. So what that means is we have to think a bit more carefully about how we want to stagger updating through the system. So what we end up doing is we fit a value function to the derivative. We approximate using neural networks the derivatives of the value function. We also need to approximate what's happening with this price, for which we cannot get a closed form solution. Okay, just that one, okay, which is the value of the price and then the drift and volatility of the price. Okay. So we have to fit neural networks for both. And then when we do the updating, we do a partial training where we first of all train the parameters for the derivatives of the value function on the master equations, and then we update the parameters for our long-term pricing formula using Ito's lemma and the consistency equations. Okay, so you have to do a staggered update. Okay, so we get some results out of this. We can see the problem is that in this economy, you could be someone that really needs housing, but if you're very poor, in the recession, you're going to have to sell the house and then buy it back again when the expansion comes. And so we get this feature of the economy where for high wealth agents, yes, they can just own housing independently of their wealth. But for low wealth agents, here we have the rate at which you're trading. In the recession, the low wealth agents, they end up having to sell a lot of housing and face this transaction cost many times. This often makes them a lot poorer. So this gives this very complicated interaction between housing and inequality, because if you're a low wealth agent, the return on housing often looks very low compared to if you're a wealthier agent, so you have to buy and sell the houses. Okay, so I think I'm out of time, so I'm going to leave it there. We go through and we do a bunch of things there. But just to highlight this talk, I've tried to give you an idea of how we approach these distributional macro models with neural nets. What we're working on a lot is evaluating this historical housing policy. I want to leave you with a couple of practical lessons for continuous time deep learning. I think the first is that working out where you want to sample is very important. Second is inequality constraints are hard. You really want to set it up so that you have very, very continuous value functions with derivatives everywhere. Enforcing shape constraints or rescaling is quite important. You need a tighter tolerance and finite difference to get higher accuracy. That's it. Sorry, I think I went a little bit over.
Please feel free to ask Jonathan questions during the break. Thank you very much.